I would like to present to you Mr. Philipp Amir Chhadeh, if I pronounce correctly, from the Technical University of Darmstadt. That must be the group of Jens Schneider. He has been introduced to me before as the 3D specialist, 3D printing specialist of glass, and I think he particularly applies the additive manufacturing technology to flat glass. So please, the floor is yours.
Thank you very much. Okay, yeah. Thank you for joining my talk. The topic I brought today with me is an investigation of the joining area of additive manufactured glass structures on flat glass. I did this in cooperation with Kodos Sleiman from the Laser Center Hannover. I work at the Glass Competence Center in Darmstadt, and yeah, there are many of us here. Come talk to us later. What I'd like to show today is I'd like to give a brief introduction and motivation, what drives AM glass. Would like to show examples, what division is in additive manufacturing glass for facades. Then I will show some experiment and testing we did with additive manufactured glass components. And then I would like to give a brief outlook on what we have to do and what could be possible to do in the future. Yeah. My research motivation or goal is to research at additive manufacturing of glass components and the application in the built environment. So with this Venn diagram, no, sorry, there's no laser pointer. This diagram shows like the material I look at is glass. The process I'm interested in is additive manufacturing, and the application we are looking into is the built environment. This excludes many processes. There are laser sintering processes of powders where you can produce very small-scale objects. This is not what we're looking for. We are looking for glass be printed onto glass. We in the built environment have the most experience with flat glass, float glass for the most of us, and this leads to the idea to print a 3D object onto flat glass and seek applications for this. What we strive for is homogeneous connections, have individualized or customized glass structures, and we want to eliminate the different materials. So we just want to do all glass solutions here. So this leads me to the vision we have in the future. For example, on the left side, you can always see the conventional object. For example, the point fixations. You have, for example, boreholes or glued connections with silicon. We have, for example, we have thick laminates. We can see from other projects we always need multiple slabs of glass, but with additive manufacturing, we could add stiffeners on glass. With this, we could reduce the total amount of glass needed, just as an idea. Also, additional idea, for example, for vacuum isolated glazing, the spaces could also be printed dots out of glass. And since VIGs need a strong edge sealant, a stiff edge sealant, you could also think about trying to fuse those two glass plates on the edge with glass onto each other. To get further into additive manufacturing of glass, we need to understand the viscosities of glass. Yeah, which leads me to this slide. I brought this diagram with me today. They are the three most commonly used glass types: soda-lime glass, borosilicate glass, and quartz glass, so silica glass. You can see the behavior of the viscosity over the temperature. And this is what's important for us. So this is what we try to understand is if you have a glass plate here on the right side for you, we want to fuse glass onto that glass. We need to have a joining viscosity at that point. And this viscosity is somewhere in the area between 10 to the power of 4 and 10 to the power of 6 decipascal seconds. And this is what we need to generate a joint. For the most common glasses, for example, soda-lime and borosilicate glass, this is not as easily achievable. You need to heat the glass plate to the glass transition temperature to avoid thermal shock. Yeah. I will just push this to the side and show some preliminary investigations we did here. Yeah, so we put 2 glass strips onto each other and put them in an oven and heated them to different temperatures. What we were looking at were the measurements on the top right, so we want to know how the angles behave, how the radii behave, and we did at different temperatures. For example, at 775 Celsius for soda-lime glass in this example, you can see that you have very sharp edges. Again, and you can still see the interlayer between the interface between those 2 glass strips. At 800 degrees, it gets a bit better. It gets smoother around the corners. You can see that the interface disappears a bit. But just at 825 degrees Celsius, you can see that the plate itself loses its shape. This is something, so from this knowledge on, we try to work further and try to find this area of joining viscosity. Now also you can see here the red dotted line, that's for quartz glass. You can see that the softening point and working point and the area of joining viscosity is way higher here in this case. You need more energy to melt quartz glass. So why would you use it? And the reason for this is quite obvious. The thermal expansion coefficient is very low with 0.5, 10 to the power of -6. So there is no thermal expansion, and the thermal shock behavior of quartz glass is very good. This leads to the additive manufacturing process I would like to introduce today and show today. This is the laser glass deposition process used at the Laserzentrum Hannover. Yeah, it's a small town in the north of Germany. Yeah. You can see the sketch on the right side. You can see their products they print. They print on a quite small scale. So those cones have a diameter of 50 millimeters at the base and are roughly 50 millimeters high, just for you to have scale. They use the laser approach, a C2 laser. They, they point the laser through mirrors to the glass plate, and there they have on a fiber conveyor. They have quartz glass fiber, which is 0.4 millimeters thick, so very thin fiber. Feed it to the point where the laser is, and then they melt it there, which is also a bit better shown in the next slide. We can also see the specimen we looked at for this investigation. So the fiber feeds so the conveyor feeds the glass into the laser beam, where the glass absorbs the energy from the laser and hits the viscosity in the range of this area of joining viscosity I showed earlier in the slides. With this, they managed to print those small walls on a glass plate, and this will be our specimen. As you can see, this is very small in diameters and size, which are, most of the current 3D printers are still small. They're printing on sheet sizes like a paper. So we thought about, okay, what are applications there? And the envision applications in the short term are point fixation, for example. On the right side, you can see a spider connector, how you could connect glass to a substructure. Or you can also think about a staircase console, where the riser rests on top of a console printed off glass. I would like to talk about this example and then lead to the experimental investigations. If you look at the forces on a normal staircase, we have the dead load, we have of the triple laminate, we have person load and single load, which then divides into the 2 consoles on the left and right. So, but this is in this case the force just drafts directly down parallel to the glass plate. This leads to our investigation. And what do we want to test? We want to test on those AM glass walls. We want to introduce the shear loading here. And the question we like to answer is, with these tests, is can load be actually transferred through this additive manufactured bond to this component? Is it a homogeneous glass component? And how does the crack and failure pattern behave? First things first, we had to check for residual stresses in the specimen due to it being quartz glass and the the residual stresses could be annealed in a tempering process. Then we did a CT scan and also photogrammetry scan of the objects. So we have the digital twin, you could say so, of these objects. What we're looking at is in the bottom right. We're interested in the shape and the contact angles at the bottom. And just for you to know, to have a scale, the glass plate has roughly a scale of 25 by 50 millimeters, 4 millimeters thickness. And this wall is 24 millimeters long, 6 millimeters wide, and 4 millimeters high. So this is the dimensions. We especially invented a shear test. We looked at steel constructions. How do they test their stuff? We just invented a cantilever system where we support the AM glass wall on a lead strip. So you can see it best in the section view on the right. And then the actuator pushes the glass plate downwards, which introduces a shear loading in the joining area. This, for this to know, is the lead strip beneath the AM glass printed wall is a bit shorter to avoid having complex stress states in the corners. So we also still would like to know what's happening, so we try to come up with equations. And so we calculate the shear stress and also bending stress. The bending stress is happening, of course, because there's an eccentricity between the support and the load. So there's bending happening in some capacity. But yeah, we're also looking at shear here, and this is the equations to do that. The next slide would be the results. We only have a small amount of samples. We only have 10 samples. You can see that the maximum load, I think the maximum number is roughly 3.5 kilonewtons. The minimum number is 2.2 kilonewtons with a mean value of 2.9 kilonewtons, which could be applied on this glass strip in a shear loading scenario. But you can also see that they have a high standard deviation and a variation of coefficient of variation. Sorry. This has multiple reasons. If we know that glass is a brittle material and that it's always deviates a lot, but we also have due to the issue that not every wall is the same. During printing process, we have a high deviation here, but we also calculate the 5% factor value, which is around 1.8 kilonewtons. But to get to the to come back to the staircase scenario, the load applied into this console would be 1.6 kilonewtons from the image I showed earlier. So we are in a range where we can say yes, we can apply load on an AM glass component into a glass plate. So we could say now, okay, this can transfer 1.8 kilonewtons. This is better than silicon or glued stuff, but it's difficult to say so if we don't understand the crack pattern, and we also know that silicons or other connections have also the advantages. It's less stiffer, for example, the silicon in this case, and also lots of the stretch states then in the component will be dependent on the support, on the type of support or the bearing. But let's go to the crack occurrence and failure pattern. We used the digital twin we had to do a finite element analysis here on the bottom left. There are two spots where the crack most likely to occur. These are multiple FE models laid on top of each other, so those are the most two common spots where the glass should break, indicated by the FE analysis. On the right side, it's difficult to see. It's a top view of the AM glass component where the crack should occur and did occur. Here you can see the section view of this, where we try to figure out the fracture mirror. You can see the lancet cracks. So we know where the crack occurred. Now the question is, how does the crack develop? We know from our studies that failure in glass happens where tension and surface defects overlap. And the question is is this contact angle, is this a surface defect? We know that the surface changes, so we have a small surface where a lot of force has to go through. So this also indicates the crack origin. And we know from other shear tests on other brittle materials that this opening angle of roughly 70 degrees is the same as the literature says. We have two cases which occurred, case 1 and 2. Case 3 didn't occur, but we cannot neglect this failure pattern since we have such a small sample amount. But I would like to talk a bit more case 1 and 2. Due to the loading, we have a mode 2 failure indicated, but then after crack opening, the crack always goes through the least resistance, and since the mode 1 fracture toughness is weaker than the mode 2, the crack propagates then in mode 1 in two different shapes, either through the glass plate or in a crescent shape to the other side of the glass wall. This is quite important for redundancy in the future. If we want to have a safety concept for AM glass, we have to consider those two cases of failure of AM glass components. So this is what we did currently. What's next is the question I have to say now. Of course, we want to investigate different stress states in the AM glass components. We have different tests we would like to do, for example, double ring bending test, 3-point bending test, or a cantilever test. Especially in the cantilever test, you have there's a higher stress state in the AM component itself. The other ones are rather testing the joining area. With this knowledge here, we then can develop redundancy mechanisms and for different failure cases. But we are sure that other applications in all our minds will come up if the process is further along. So there will be problems we are not even aware of we can solve then with AM glass. But in order to do this, there's also the second thing we have to work on is we have to upscale the AM glass process. We want to go to the left. We want to use additive manufactured glass, AM glass, to build facade panels in a building, but we're on the right currently. We have small-scale printing options, but we need to find a step in between. One step would be to build something like the second picture from the right, to print only on some part of the glass. What could also be done is to have a full printer, which is a large size and can print on full flat glass sheets. And the other option, say, would be to print onto freshly produced glass in a float line, which often is denied since the float line process is not touchable. But this would be an option for we have in mind for the future. I would like to thank you for listening. I would like to thank Glassstone for having us, and also like to thank the technicians for doing all this. Thanks.